Saxon Algebra 2, Lesson 54. Hi students, buckle in, get yourself a drink of water. I'm here to rock your world a little bit today. We're going to start with something called polar coordinates. Now, we've been graphing for a long time. And in that respect, you'll be familiar with what we're going to talk about today. Let's take a very simple, straightforward point. 4, 2. You know how to graph this. You've been doing this for a long time. You recognize that this follows a pattern where we call the first value the x value, the second value the y value. You recognize that this is the x-axis, this is the y-axis, right? You recognize that we measure basically a number line, right? It's just a number line, that's all it is, on each of these. And I'm gonna fill in some of the points that I want. And to graph it, we go to 4 on the x-axis, and then we follow that up to 2 on the y-axis. And at the place where those two lines meet, usually we just visually make that line, right? We don't actually draw out the dots usually. That's where our point lies. And that's why we call these rectangular coordinates, because we kind of make this little rectangle, like I said, usually with our eyes, not with our pens, as we go to find them. Now, there's one method that we're going to continue to use. We are going to specifically call it rectangular coordinates, and we're going to write the same point this way. We're going to positive 4 on the right axis and positive 2 on the up axis. Yes, we're going to essentially rename the x-axis and call it R for right. When a point lies on this side, we write positive 4 in this case. If we were going to negative 4, we would write negative 4. So this is the positive R and the negative R, just like this is the positive X and the negative X. All right, so we're gonna write the x-axis as the r-axis, and then the u becomes the y-axis. Okay, so we'll simply relabel these R and U. Okay, right, not a huge change. This isn't the lesson for today. Notice these are called rectangular coordinates also. We can call our old way rectangulars, but we can also call this new method rectangulars. Let's do one more point, and let's put it over here. Let's use -2 - 3. This is the old school way of writing it. Well, let's see, we go to -2 on the x-axis because we know that's the first one. And then we go to -3, which is down here, and we plop the point right there. Same methodology, except we're gonna rewrite that as -2 on the right, -3 on the up. Okay. So this now, when we say rectangular coordinates, this is what we mean. This kind of new way of writing what's familiar, okay? We're calling that rectangular coordinates. Now let's talk about polar coordinates. As always, we start by reviewing pertinent information that we already know, right? That's how I make sure that you'll be standing on solid ground when I hit you with the new stuff, is I remind you of what you already know. Now we can talk about something new. Now, instead of seeing our same Cartesian coordinate system, instead of seeing it as two number lines that overlap, we're going to talk about measuring it in terms of degrees. Each quadrant is worth 90 degrees, right? That makes sense because they make a perfect right angle. but we're going to lean heavily into these degrees, and we're going to measure starting here up and around, as the case may be, you'll see. But we'll always measure in this order, and we can remember that this is the starting place by thinking of this as the horizon. Polar coordinates are used very often by seafarers, air navigators, and if you listen carefully to the chatter, whenever there's a pilot talking in a movie, for example, you'll hear things and now you'll realize, oh, they're talking in polar coordinates. The irony is that when navigators use polar coordinates, they usually start from up here. It's us mathematicians that like to put the starting place down here, which you would think the people who are actually navigating outside in the real world would do the same thing, but they don't. They start up here, but that's okay. We're not going to talk about that anymore. But just irony, whenever you think, oh yeah, I start here because it's the horizon. This is our starting place. And this is where we measure up and around. I'll say more about that in a minute. What we're going to do is write our coordinates in a completely different way. And it's a little shape that looks like this. And then these blanks are where we would fill in the information. In this box, we will write what we call the direction. Whoops. And we will measure at that as an angle. Okay? So what we'll do is we'll say, we'll be given a degree measurement, and then we'll find that on here. That will give us a direction, and then this will be a distance. And as you'll see, this will be the hypotenuse of a triangle. Don't worry, hypotenuse. These two things I'm going to explain further in the next problem. I just want you to see that the way we format our polar coordinates looks completely different from either the original way or this newfangled way. These two look a lot alike. This is a completely different beast. So let's go into more detail about how these polar coordinates work. Problem 54.1. It says change 4 at 57 degrees to rectangular coordinates. All right, so we somehow have to figure out what that means, and then we have to figure out where that point sits, and then we have to rewrite it as rectangulars. Don't worry, it's not as hard as you might think at first. So what I'm drawing is the basic system, and I'm remembering that each one of these is worth 90 degrees and that we start here from the horizon. That's what I just told you. And remember, my arrow went this way and came around. All right, so what we have to do is we have to figure out roughly, we're just sketching, roughly where would 57 degrees be? Well, let's see. How far would we draw a line that was 57 degrees away from this horizon? Well, we know all of this is 90. And 57 is close to 60. 60 would be 2/3. So I'm just going to sketch a line in right about here. And then I'm going to call this 57 degrees. Okay? Now I'm going to make a line come straight down and turn this into a right triangle. And I'm going to say this is where my point sits. Now, that is how I take care of the 57 degree part of this. How do I show that the hypotenuse is 4 units long? Here's the fun of this. There's no grid on here. So we can make this distance here that I've drawn, we can make that be whatever we want. So we're just going to say, yeah, that's 4. Yep. If it was 86, I could just write 86 here. If it was 1/2, I could write 1/2 there. We don't have to use a scale to graph the hypotenuse. We can just put it in however we want. So what I've done now is I have drawn the point that matches to these polar coordinates, right? It's that right there. Okay? Our next step, so let's see, to graph this, here are my tips. Start with the angle. Whoa. Remember that the angle shows you the direction. That's the number that is inside this boxy thing. And these are kind of like bullet points. And that all you have to do is estimate it. And here comes the important part. And label it. Writing 57 degrees in this little corner makes it true. Your sketch doesn't have to be perfect. You don't have to measure this with a protractor or anything. You just do your best to estimate where that angle is and go on from there. Okay? Then we're going to then we drew the hypotenuse. It's the number that is outside that little polar coordinate sign. It's 4. And there's no need to measure. It's quite freeing once you get past the weirdness of it. Okay, and once we draw that hypotenuse, then the third step is once you draw the hypotenuse in, then you draw a straight, make it as long as you want, and you'll see, we just make it big enough so we can write around it. Then you draw a straight line down to the horizontal axis, and that, when you do that, you make a right triangle. Now, making this right triangle is very, very important, because notice what we need. In order to make a rectangular coordinate, we need this length and we need this length. Or no, I'm sorry, we need it over here, don't we? I'm gonna get to that, right? This will be our R value, and this will be our U value. Notice that those two numbers that we need correspond to if this is our angle, this number, the first one that we need, is the adjacent side of the triangle. And this number, the second one that we need, is equal to the opposite side. So if we use trig values to find the lengths of the two sides, we'll be able to take that information and write the rectangular coordinates. So, welcome to the world of trig, where we use our trig functions to solve interesting real-life problems. All right, the trick here is now we're going to use cosine first, and I'll remind you of why, then sine, to find R and U values. Remember, we want to find them in this order. We want to find the right and the up in that order because that's the way we write them. So we always use cosine first because cosine uses the adjacent side, and the adjacent side is the one that's equal to the right. Then we'll use the sine function second. Sine is opposite, right? Oscar had. That will give us the value on the up axis, right? Notice this is the number we want, but it corresponds exactly to the side of the triangle. All right, so we always use cosine first and then sine. So here's what we can do. We know that the cosine of 57 degrees is going to equal our adjacent number over our hypotenuse, which is 4. We can quickly reformat that. We can pop that up, right? And we can say 4 times the cosine of 57 equals, and now this is ready for the calculator, right? We enter 57, then we hit cosine, then we multiply by 4, and what we get is that A equals 2.16. All right, I worked that out ahead of time. Make sure, grab your calculator right now, pause me if you need to. Make sure that you can do this calculation and get the right answer. This is rounded. This is not the way it looked in the calculator. It had a big long string of decimals. But I rounded it to 2.16. So right now, pause me and make sure you can calculate this before you go on. Okay, now we're ready. So we know that this is 2.16. Now let's do this side. For that, we're going to use the sine of 57 degrees equals the opposite side over 4. The hypotenuse is the same both times. We'll do the same thing. We'll pop that 4 up here so it's a coefficient. That will be equal to O, and then I'll solve it. O equals 3.36. Okay, notice that both of these numbers turned out to be positives, which makes sense because our point here is in the first quadrant, so we know positive, positive, right? All right, and so the very last thing that we need to do, I think I'm going to write it up here, is write these rectangular coordinates. They're both positive, so we would say plus 2.16 on the right axis plus 3.36 on the up axis. That is the very same point as what we were given in the first place, right? These are the directions that help you draw the triangle. And then once we get the triangle set, we use trig functions to find the lengths of the missing sides. We're gonna do this a ton. You'll get used to it. You'll start to think this is really super easy, all right? These are my best tips to help you draw that triangle, and we always start by drawing the triangle. All right, we're going to do 2 more to help you cement this. We're gonna follow these steps and this. I will talk you through them, but you have them, excuse me, you have them written for future reference. 54.2. Change 7 at 230 degrees into rectangular coordinates. Now, sometimes when students see the big number in there, they panic. Don't worry, it's not any harder. Our triangle is just in a different place. Remember, we always start here at the horizon. We start measuring. This is the right, this is the up. We're gonna switch it to that. We need 230 degrees. Well, let's think, these are each 90, right? So when I go from here to here, I've gone 90 degrees. I need to keep going. I go this far, it's another 90 degrees, so I'm at 180 over here, right? Now, if I go another 90, it's gonna be a full 270. So I know that my angle lies somewhere here because it's between 180 and 270. Let's see, 180 plus 50 equals 230, right? I'm figuring out how far I need to go. It's a total of 90 degrees. This much is 180, so I need another 50, so that's gonna be about like this. Now, the reason we do this is important. This whole thing from here all the way to here is 230 degrees. That's the right place. But I specifically need to know this angle. Well, that's 90, that's 90. I'm just writing down what we already talked about. That much is 180, so this is a 50-degree angle. This is the angle we will use to calculate our trig values. We will not use the whole thing because that's not a triangle, right? We just want this little piece down here. So now I follow my own directions, which say, draw and label the hypotenuse. Okay, I did that. And that is 7 units long. Again, there's no scale to this. You can make it however you want. There's no need to measure it. And then we drop a straight line to the horizontal axis. In this case, I'm coming up. Okay? Wherever you finish drawing, just take it back to this line. That used to confuse me because sometimes I wanted to take it to this line, like I wanted to draw it over here. Well, I understand that, but we just don't, all right? We always take it back to the x-axis. Now, I've got a right triangle, I've got an angle, and I've got a hypotenuse. I'm ready to start calculating my trig functions. Remember that cosine we always do first because that gives us the adjacent side, which is the right, and we want to write that first. And then we'll use the sine, which will give us this side, which will be equal to the distance on the up axis. It'll be a negative up in this case. All right, so we always start with cosine, so we can say that the cosine of 50 degrees equals the adjacent side over the hypotenuse, which is 7. And we can flip that around and say that 7 times the cosine of 50 degrees equals A. And again, with your calculator at hand, enter this, put in 50, then hit cosine, then multiply by 7. Okay, times 7. And what you should get is that the A value is 4.48. We're rounding to 2 decimal places. And then we do the same thing with the sine value. The sine of 50 degrees equals, where am I? The sine of 50 degrees equals the opposite over the hypotenuse, which is 7. That's an O, not a 0. And I can do this. This is adjacent and this is opposite, just to help you remember. Keep yourself oriented. All right, then we flip the 7 up. I am going to start, from now on, I'm not going to write this calculation as a fraction. I'm going to immediately put the hypotenuse as a coefficient in front of the trig function. All right? So this is how we started. We use those ratios that we learned way back in the very beginning, right? A over H, right? Cosine, Oscar had A hold. But we're experienced enough now that we know that hypotenuse is going to come up here and be multiplied. And so we can jump right to that calculation. Same thing here. I don't have to write the fraction. I can jump right to this. It's kind of the second step. And then I multiply and I use my calculator, 50 sine times 7. The value for O is 5.39. And then the last step is to simply write out the rectangular coordinates. I'll write them down here where I have a little bit more space this time. And they would be let me show you one more thing. I like to do this because it helps me stay oriented and remember what shape I want my answer to be. And sometimes I do this way at the beginning of the problem. I write room for a plus or minus sign and a value. That's going to be the right axis. Another sign, another value, and that's going to be the up. This gives me a format. And as I'm working, I remember this is what I'm trying to fill in the blanks. And here's why I'm telling you this, because soon we're going to get this and be asked to go back to that. And your brain gets scrambled because you can't remember where you started and where you're ending. So I like to draw a picture of my answer. That helps me remember what I'm doing as I'm working. Now I can fill these in. The right value is the adjacent value, and it, I can see, is going to be a negative, isn't it? Because I'm on the negative rights. So it's negative 4.48 on the right. And then what about the opposite? That's also going to be a negative, all right? So these calculations will always be positive. We have to use our own brains to figure out if they're positive or negative in real life. This value is a negative, so I write negative 5.39 to the up. And guess what? That's right. I don't think, let me double check that one and make sure that's right too. 2.16 positive, 3.36. Yes, this is correct also. Okay. All right. This problem is going to become like breathing to you. I promise. And we're going to do one more right now. And this one I'm going to do the way I would like you to do it in the homework. We'll just cut to the chase, right? Okay. This is example 54.3. And the angle we are asked to find, it says change 42 at 340 degrees to rectangular coordinates. Now, these numbers are a lot bigger than what we started with. Don't panic. It's not any harder. We always start by drawing the picture. We start here to measure our degrees, which is what we do first. We're going to go up and around. We know that the whole circle is 360, right? So that tells us that we want the whole circle except for 20 degrees. So 20 degrees is just a little bitty sliver. So I know that all of this is 340 degrees, and this is 20 degrees. Again, kind of because I say so, right? I'm the one drawing the picture. I want it to look realistic, but it doesn't have to be perfect. I draw the hypotenuse out as I mark the angle. I can make it as long or as short as I want. That looks pretty good to me. And I'm gonna say, oh yeah, this is 42 degrees. I'm gonna put a little circle there so you can tell which one's the hypotenuse because it's starting to get kind of cluttered. And now I draw that, I close the triangle by going back to the right axis. That's my right triangle. Now I've got a triggable picture here, right? The 340 degrees has nothing to do with my triangle specifically, but it's how I found the 20 degrees that I needed for my triangle. So you have to let your brain kind of wrap itself around how these angles are measured out and then what kind of a triangle we want, right? I don't want the 340, but I like this little 20. This is what I need. All right, to find, remember we have the adjacent equals the right and the opposite equals the up. It is very helpful to write this as you're getting the hang of these, so please write that down so that you'll be able to keep track of what the heck you're doing. We'll do the adjacent one first and we'll use cosine. So I'm gonna write the hypotenuse first. 42 times the cosine of 20 degrees will give us our right value. I was writing A's here. I'm gonna, because that's what we're used to, but now you're ready to shift, right? A equals R, so it doesn't matter, but this is what we're trying to get. Let's do this too, this will help us. I'm gonna draw the box of what I want my answer to look like. I want a sign and a number for the right value, and I want a sign and a number for the up value. I'm not gonna fill it in yet, but I just want to know how that's gonna work. Okay, I grab a calculator, I enter 20, I hit cosine times 42. Remember that with our calculations, when we take them to the calculator, we're often working backwards. That's just a rule of thumb, a tip I can give you, is very often we're working backwards. And we will get a right value of 39.48. Okay, that sounds about right. If this is 42, for this one to be 39.5, that sounds about right, doesn't it? We can check our answers for reasonableness, just going, okay, well, if that one's 42, this one should be pretty close to it, but not quite as big as it. That sounds really good. This one we would expect to be quite a bit smaller, wouldn't we? We're not going to be as close to 42. This one should be, I don't know, maybe 15, something like that. And we'll use sine, right? We always use cosine first and then sine because we want the adjacent side and then the opposite. And we have been saying this equals the opposite, but now I'm going to say the u because it will remind me of where they belong. We enter it into the calculator, 20 cosine times 42, and our up value is 14.28. You guys, I did not look at that answer. I just guessed. Granted, I have done this problem, I don't know, close to 20 times over the years, but anyway, this is a reasonable answer for this. If this is 42 and this is 15, that seems about right. This should be a lot smaller. All right, now all we have to do is an art project. We copy it in. Now we have to think about positives and negatives because remember our calculators are always going to give us a positive value. We have to use our own brains to figure out if they're positive or negative. This side is a positive value. So it's a positive right value, 39.48. This up value is negative, right? It goes below. So this is a negative, and it's 14.28. Guess what? That's the right answer. And it's nice because we already have a nice box around our answer because we drew that ahead of time. Again, I like to draw this at the beginning of the problem because it reminds me, it's literally a fill in the blank then, right? It reminds me of what my answer is supposed to look like. And it also helps me remember what the heck I'm doing. Because sometimes when you get into the middle of all this, it's easy to lose track of what it is that you're even doing and go, I don't know. Where am I headed with all of this? Especially as we start doing different types of problems involving these pictures. So we are now done with this. We have a short, smaller section on geometry that will go in a completely different gear. This is trigonometry. This is trig, okay? So when you are doing these problems, feel smart, feel proud of yourself, all right? Okay, one more short topic. This will ease your brain. The topic is similar triangles. Now, we haven't talked about those in a while. I know that the problems have still been filtering through your homework, but let me remind you that similar triangles have the same angles, but different sides. That's the definition of what it means to be similar triangles. Because we know this, we also know that they are proportional, which means proportional, which means we can solve for missing sides, right? But this time, we're going to do something different. We're going to work them with letters only, and we call that abstract similar triangles. I didn't want to tell you that word in the first place because I didn't want to freak you out. Okay, John draws a picture for us. Cute little bow ties. It's a crooked bow tie, but it is a bow tie nonetheless. And he draws us a picture that looks like this. He writes A and B, C and D. Now, how do we know that these two triangles are similar triangles and are therefore proportional? Well, John tells us that these two angles are the same. And we see these guys are vertical, so we know that those two have to be the same too. If two sets of angles match, then we know the third ones must as well because they have to add up to 180, right? So when we see these markings and notice the vertical angles, we know we've got proportional. Our next step is to redraw, which I always recommend with these pictures of proportional angles so that we can properly compare these guys. So what I'm gonna do is I'm gonna draw the first angle pretty much the way it looks and this will be that angle, and this will be that angle. A is this side, C is this side. Now I'm going to redraw this little triangle. It didn't work out as perfectly as I'd hoped. But we want this angle to be here and this angle to be there so they'll match, right? So now I have to mentally go over here and go, okay, so how is it? The side opposite the 1/E is D. So there's the 1/E, so that means this is D. And B is between the 1 and the 2. So there's the 1 and the 2, so this must be B. All right, notice that we're leaving this third side, this third pair of sides, unlabeled. It's fine. Now, the second step is to set up our proportions. Now, the way I do that is I like to go A times B equals C times D. That's what looks logical to me. Right? I compare the sides on the two triangles, keeping this triangle always in the top, this triangle always in the bottom. A goes with B. Oh, I'm sorry, I wrote this the wrong way. A over B equals C over D. This isn't right. Sorry. That's a proportion. That's not a proportion, right? Okay. So I listed the fractions as pairs of points between the two triangles. I kept this one in the hypotenuse and these in the denominators, right? Now, what's interesting is John does it differently. John says A over C equals B over D. He goes, this big side over big side equals little side over little side. Now, here's the thing. Neither of us is wrong, because once we do the next step, which is cross multiply, notice that I get AD times BC, or AD equals BC, right? We cross multiply like so. AD equals BC. Look what happens to John's. AD BC. We both get the same thing, all right? So however you choose, whichever of these methods makes more sense to you, I much prefer this one, honestly, because we've always gone back and forth between the triangles. You'll get the same cross-multiplied equation no matter which of those you choose, all right? But just do it this way because it's better. All right, now that we've got this cross-multiplied equation, the pages in this lovely new book of mine are so thick. AD equals BC. I'll put that up here. Now, we can solve for any one of these letters that we want. So let's say that we're asked to solve for D. Okay, I don't know why you would want to, but we can solve for any one of them. We would simply take our equation and we want to isolate D, so we would just divide by A. And so then our final answer would be D equals BC over A. So we can use abstract values for the sides and still calculate the length of the sides. It's not a very satisfying answer, but this would be the length of side D in this abstract triangle of ours. All right? So the moral of the story is, and this is correct, the moral of the story is, don't let the fact that these are letters instead of numbers freak you out. It's fine. Just go ahead and do the same thing that you would do. Set up the proportions, cross multiply, and then in the last step, just solve for whichever letter it is that John asks you to. There's nothing magical about side D. That's just the one John chose and said, hey, solve for D. If we want to solve for D, we would divide both sides by A, right? Just to get D by itself. Okay, that's just a little side note to keep you on your toes. That's the end of lesson 54. By far the most important part is our polar coordinate business. We will be coming back to that for years. So enjoy, feel smart, and I will talk to you next time.